Good afternoon. Welcome to the fourth Pancharatnam lecture. This is a special series of colloquium level lectures that we have been holding to honor, in the honor of Professor Pancharatnam, a very illustrious alumni of the Raman Research Institute. So, a few words about Professor Pancharatnam for those who have come here for the first time. Professor Pancharatnam joined the Raman Research Institute as a senior scholar in 1952. He completed his PhD under the guidance of Sir C.V. Raman. Professor Pancharatnam was interested in crystal optics and discovered a subtle effect in the interference of polarized light. This discovery is recognized as an early precursor of Berry phase in quantum mechanics, and this aspect pertaining to the geometric phase that is both relevant to classical and quantum optics literature is often referred to as Pancharatnam Berry phase. RRI has continued to be very active in this area, which is now an important area of current research, and it is also, I'm glad to say, area of national interest with the national mission coming up. Professor Pancharatnam passed away in Oxford in 1969 at a very young age of 35. So let me introduce the speaker today. So it's my great pleasure to introduce Professor Joseph Salk. Joe Salk is an eminent astrophysicist, cosmologist, and I would say rightfully a living legend in modern cosmology. I mean, he has authored many seminal papers, and many of us work on results that were first obtained by him. And he has also written many papers that have triggered new directions in the field. And to the broader audience, his semi-popular book, The Big Bang, is still the book I recommend to any high school or early undergraduate student who wants to read up about cosmology. It's an excellent book. And I also had the pleasure to first meet him and his amazing research group in Berkeley in 1992, very early in my career. And I must say that the group was amazing because every person that I saw in the group, the student and postdocs, have gone on to be really stalwarts in the field. And this, I realized in later years, has been a hallmark of Professor Silk. He's worked with younger people, he's mentored them, and you know, starting from people like I don't know, with Dick Bond and Iftashu were George Iftashu. No one, everyone knows, were postdocs with him at some point. And so there's a very rich legacy of students and postdocs besides the legacy of his work that marks him out in the field. He obtained his PhD in astronomy from Harvard in 1968, and his first position was at Berkeley in 1970, where he became the chair of astronomy in 1978. And after 30 years there, he returned to UK to take up the Savilian chair of astronomy at the University of Oxford. He is currently the professor of physics at the Institut d'Astrophysique de Paris, and then also at Johns Hopkins University as a Homewood professor of physics and astronomy. And he is, again, to reiterate, he's a leading person in the field and also quite visionary. And I'm really glad that he's here to give you a glimpse of what's to come in future in cosmology. Over to you, Joe.
Thank you, Tarun, for that glowing introduction, which I don't really merit, but anyway, here we are. I'm going to discuss the future of cosmology, and I'm going to argue to you that our future will lie in building telescopes on the moon, and I'll try to explain why I've come to that conclusion. So let's just take a step backwards. The foundations of modern cosmology were certainly laid down with Georges Lemaitre, who was really the fundamental figure, the founding figure in physical cosmology. It's true that Friedman co-discovered with him the solutions to the expanding universe of Einstein's equations, but Friedman went on to think seriously about the components of the universe. What slowed it down, that was dark matter, and what seemed to speed it up, something we now call dark energy. In fact, that's pretty much what Lemaitre called it. He talked about energy in the vacuum from quantum vacuum fluctuations being non-zero and giving you an effective equation of state, P equals minus rho c squared, and therefore giving you acceleration. And this, he said, was the meaning of Einstein's cosmological constant, which was the basis for his models. And frankly, we haven't really advanced in all this time very far beyond that in terms of any further understanding of the origin of the acceleration other than this idea of vacuum fluctuations. Okay, so all this was done around 1930, remarkably, and modern cosmology took off rather slowly at first as observations got better, and then around 1980 there was a revolution in cosmology. The first new model since Einstein, Lemaitre, the glory days of cosmology, the ideas of inflation were developed. I'm going to say a little bit about those. But let me just give you, first of all, the backdrop, the history to the modern universe. And so basically here we are today, looking back in time, we see structure develop, galaxies forming, going back further in time. There was an epoch where the first stars formed, we call that cosmic dawn. And even before that, there were the dark ages, there was nothing, except that there really were hydrogen clouds, hadn't yet collapsed under gravity to form stars, that were the building blocks of the later galaxies, and there were many of those. And then going back further in time to some 400,000 years after the Big Bang, we come to the microwave background, which we can see imprinted on the last scattering surface of the universe, where they last Thomson scattered and give you fluctuations, slight deviations in temperature, which are indicators of the seeds, the density seeds from which all structure formed today. And before then is this epoch where things began with an enormous explosion of expansion in the first 10 to the minus 36 seconds after the Big Bang. That is our basic story. And I've put three big question marks on the picture. One is the current universe is beginning to accelerate. That's the cosmological constant at work. We don't have a good theory or an understanding of that. We have the dark ages, the new frontier in cosmology. Before the galaxies form, we haven't even begun to penetrate that yet. And that surely is where the keys are to our beginnings, because those are basically the roots, the seeds from which all structure formed. And then finally, way back at the very beginning, the universe underwent this dramatic expansion to explain why it is so large now, where the fluctuations come from. And that is a wonderful theory, but we don't yet have any definitive proof or that this theory actually is valid and did explain the beginning. So these are the goals then in cosmology today, to try to understand dark matter, dark energy, to explore now the dark ages for the first time and get a better grip on our origins. And I think the results are not very satisfying at this point in time, because we have not met very much success in these grand goals. So first, a few words about inflation. It was a wonderful theory. It had a revolutionary effect around 1981 when three independent groups developed this idea. But since then, it's waiting for proof, as it were. Okay, and we have many ways to try to get there. I'll explain one or two of them to you. But above all, we need some verification. And I'll explain to you where we're going on that, which at the moment is not very far nor very fast. And I'm going to argue that we need to do something about that in modern cosmology. Okay, so why is it that I'm a little bit pessimistic about where we're going with dark energy and with dark matter and with inflation? So I'm going to not explain any of this in any detail, but just give you the general idea that we are searching for dark energy by measuring the acceleration of galaxies in the universe and the amount of dark matter in the universe. We're going to test our model, basically. There are certain predictions as to what those numbers should be, and this basically revolves around Einstein's cosmological constant, or this famous equation of state P equals minus rho, the vacuum fluctuations and all that. And the remarkable thing is that despite we've now been looking for a long time, at least 20 years of modern observations, we're converging on exactly the cosmological constant. That is this P equals minus rho, that's W equals minus 1 equation of state, and the density of matter in the universe, roughly 1/3 of the critical density, which leaves 2/3 for dark energy. And so that's the model. We guessed at what it was 20 years ago when the discoveries were being made, and we've got more precision, but we've made no advances in the sense that we haven't found any anomaly that would tell us some new physics is involved. We just, and it's not obvious to me at the moment, as we build and fly our new telescopes. Euclid this July, the Raman telescope in a couple of years, and the LSST, the large ground-based 8-meter telescope. All of this stuff, amazing, will make amazing surveys, get more results, but there's no guarantee that we'll learn anything fundamental new about cosmology. We will get more precision, that's for sure. But, you know, we want to do more than precision in cosmology. We want, you know, to zero in on an understanding of our model. Okay, so the microwave background. That's been another growth area for precision cosmology. In fact, the measurement of the fluctuations with increasing generations of experiments has given us a whole new outlook on cosmology, because we're sampling basically an earlier epoch of the universe, 400,000 years after the Big Bang at last scattering, and we can measure all the parameters from the structures of the fluctuations in cosmology, compare those with the ones we measure in nearby galaxy surveys, and we are finding tensions, but the bottom line is this, but maybe or maybe not, they'll go away, but they're only at the 1 or 2% level. When I began in cosmology, we were arguing by 50% what the density of the universe was. We didn't know, but now it's, you know, a few percent uncertainty. But what is important, though, is that we are looking now to test inflation, and so the gravity wave background produced that inflation. As it ends, it gives you a shearing effect on the microwave background, a polarization mode that is one of the prime predictions of inflation. We haven't found it yet, that's the problem. But the real problem is that as you forecast what it should be, there is no guaranteed value for the polarization signature of inflation. All we can get empirically is upper limits, but there's no guaranteed return. There are models which say it should come in at the 1% level, the 100% level, depending on how you define what evaluates it, the relative amount of shear in the fluctuations, but there's no guarantee of anything at all. So that's a real problem. There's no guaranteed return, yet we have these wonderful experiments, a light bird about to go up in space, stage 4 at the South Pole, doing equally precise precision measurements, increasing by tens or 100 this degree of this shear parameter, but nevertheless there's no bottom line here. Dark matter is another story that also has no bottom line at the moment. So we've found one interesting result over the years, and that is a popular candidate, still is, for dark matter. It's a weakly interacting particle, Majoron-like, which annihilates with itself, and therefore should give you a gamma ray signal if it's a massive particle in the regions where there are lots of dark matter. So some years ago, the Fermi satellite discovered a gamma ray excess some 2 decades ago in the inner parts of our galaxy. This is still our best candidate for dark matter, a glow from dark matter, but the problem is that it's equally possibly to be a glow from millisecond pulsars, which are known gamma ray sources. And we simply cannot tell the difference. So it is not a definitive test yet of anything to do with dark matter. It might be someday. It's our best indication so far. But our best bet at the moment is to look directly for the particles by doing scattering experiments deep underground, away from the cosmic rays. So we're doing these, we're building bigger and bigger detectors, and the result today is nothing. We've found no direct evidence for the halo full of these weakly interacting particles, massive but weakly interacting, that could be our best should be our best dark matter candidates. And so the real problem then is if you ask what is the parameter space we can be searching in, this is the cross-section of this elusive particle, and here is its mass. And so we've explored a tiny fraction of this mass space where, for example, there are relics of supersymmetry. We're exploring ultralight particles too, which have a motivation from QCD, and there might be something, there might not. But all these other parameters we have almost no handle on. Many, many decades of cross-section of particle mass. So the prospects for a result, if you take some sort of Bayesian view about this, or this parameter space, are not good. Nevertheless, we are searching. We might be lucky. We may find something someday, but there's no guarantee of success. Now, if you want to play the devil's advocate, you say, well, dark matter, Einstein got it wrong. There's another theory of dark matter. Well, this is something many of my colleagues are actively pursuing, and I find the results there completely unpersuasive. So in this figure, which is called modifying gravity, I show you the full scale where gravity could be different from Einstein in terms of size scale and mass scale, all the way from the horizon to microscopic scales, etc., and tiny masses, Planck masses to enormous masses. And you'll see there's only a tiny parameter of that parameter space in red where we've actually measured the universe and galaxies and have a good test of Einstein's gravity. All the rest we have no idea. So again, if you say gravity might be not correct, we want to correct Einstein, there's a lot of parameter space you have to search for, and that will keep theorists busy for a long time. Finally, another way to make dark matter is to collide particles together at very high energy. Well, the Large Hadronic Collider, roughly 10 TeV rest mass collision energies, maybe 14 TeV at the moment, has not found anything yet. The idea is you bang particles together at high energy, protons, and you look for debris that might carry off missing momentum or energy. We haven't seen these. We're proposing to build a much larger, more powerful collider, up to 100 TeV in the center of mass frame. Maybe that will find evidence for new types of particles, or we have no idea, maybe not. So there's one point in common about all I've told you. Enormous interest, momentum, vast sums being spent in all these experiments, but there is no guaranteed return. We can spend all this much, 10 times more. There's no guarantee that these experiments will give us a detection of something, okay, that will answer our fundamental questions. What is the dark matter? What is the dark energy, etc., etc.? What is the acceleration? All of this stuff. So what do we do? Okay, so normally, often in physics, when you want to really try to do something new and fundamental, you go to some virgin territory, something new which has never been explored before. And there, you may be lucky, you've got serendipity going for you, but at least in this example, I'm going to show you you're guaranteed a return, because in the dark ages, which you haven't explored yet, we're beginning to talk about it a lot, we're beginning to explore it, we haven't got there yet, it's going to take many years of effort to do that, I'll show you how in a second, but in the dark ages we can see, we're guaranteed to see, the beginnings of the galaxies, the gas clouds from which the galaxies made. They must be there, they're hydrogen clouds, they have a 21 centimeters hydrogen spin flip signal in emission or absorption. Typically in absorption, because they basically are cooler than the radiation background, we see them as shadows against the large scattering surface, 21 centimeter, highly redshifted. So that's the hope, that we might do that. Okay, the problem is the wavelength is stretched out with the expansion all the way from 21 centimeters down to tens of meters. It's a very tough problem. Here you can see the prediction of tens of millikelvin for this shadow of the hydrogen against the cosmic microwave background. Various physics comes in at lower redshifts, but look at this. This is the gas temperature seen slightly colder than the background radiation, and this will be the signal you're looking for. What is the prospect of seeing this? Well, I think it's very large, and the reason is the following: that in the microwave background, we've explored in terms of the numbers of pixels in the sky, everything there is now, a few million pixels. We're extracting all that information as best as we can, but basically you're limited by having a million bits of information on the sky. You can just do so much with that. You can do cosmology to high precision, but you can't get the ultra high precision you may need to go further. For the galaxies, you go deeper, you probe smaller scales, But the story is similar. There are a few billions of galaxies. In our newest surveys, we'll probably get 1 billion redshifts or more. That's what LSST is proposing. But, you know, the galaxies are a bit different one from another. You have to average over them. So we estimate, roughly speaking, you might get 100 million bits of information from all future galaxy surveys. That's what your limit is. Well, that's a big improvement. Factor of 100 on the microwave background. But really, if you think about it, it's a factor of the root of 100, factor of 10 improvement in precision. That's a big step, but that may be not enough to test inflation. The one place where you have a real test waiting for us in the future is by going to the dark ages, where a galaxy like the Milky Way is assembled from millions of solar mass clouds of gas. So suddenly, from one galaxy, you have 1 million components of that galaxy, which means you have trillions of modes of information on the sky for you to explore and put into your cosmological precision fitting to get parameters. So that's where the information is. It's not going to be easy to get there, to get that information, and I'm going to show you how we do that then. Okay, and we're going to see this by going to the quietest place in the radio sense in the low frequency radio universe, and I'll show you that's the best place to go to do radio astronomy. Around the Earth, it's not great because you've got the ionosphere. The moon has no ionosphere. You've also got radio interference from the Earth, which is very bad for low frequencies, especially your radio frequencies. On the moon, go to the far side, we don't have that. So this just summarizes my information argument. That's where we're going to get to with trillions of modes, bits of information in the future. Okay, so the moon. Well, here we see where we're going to go for on the far side of the moon. We're going to basically implant things there. There's only one radio instrument there at the moment, which unfortunately the Chinese put there, Chang'e 4. It was landed in 2019 with a relay satellite built by the Dutch. Unfortunately, there's very high local radio noise and was unable to give any signals, any radio signals that were of any interest. But the Chinese are going to do better very soon. So basically, when you go to this remarkable environment, radio quiet environment on the far side of the moon, what you want to do is look at roughly 10 meters wavelength. That means the sweet spot I showed you for the dip in the microwave, in the hydrogen against the background, is roughly at a redshift of 50 or thereabouts. Frequencies of 30s of megahertz, wavelengths of tens of meters. You want to look at roughly 100 times better than the resolution of the microwave background. That's not very complicated with a large enough interferometer, and you can estimate roughly what your optimal array size is to get that resolution. It's roughly 100 kilometers across, not much bigger than the square kilometer array. So again, shouldn't surprise us too much. And you need millions of dipoles to get the sensitivity, where the square kilometer array, its low frequency version, is 200,000 dipoles. So, again, we're doing very similar things on the Earth. It's just the Earth is no good for the dark ages. We better go to the far side of the moon. So technologically, it shouldn't be too complicated, provided we can get the information back. The real problems come in as follows, that the foregrounds from all the stuff in between us and the dark ages are very considerable, all the signal emission from intervening galaxies and halos of galaxies. And the problem is that this low frequency radio background, it rises dramatically to lower frequencies. You're looking for a 10 millikelvin signal, and the foregrounds are thousands of Kelvin. So it's going to be difficult to search for that. There are all sorts of clever tricks you can use. I'll show you one or two in a second. Here is one here. If you divide your interferometry search into sampling angular scales and frequency scales, different frequency scales, you can basically separate parallel wave numbers from perpendicular wave numbers along the line of sight. You can do tomography on the sky using frequency as your effective measure of distance, of redshift, if you like. So that's one way. We know the foregrounds don't have this frequency shape or spatial shape of the 21 centimeter emission from the dark ages. So you can try to sort out the foregrounds with tricks like that. So that's one idea. And so what are the plans then for doing this? Well, we should be inspired by the SKA. So here's what we're doing in space. Well, first of all, I mentioned Chang'e 4. I've pronounced it terribly, I'm afraid, but whatever. Chinese first Chinese radio telescope, a single dipole on the far side, had enormous local noise, electronic noise, didn't give us any science, unfortunately. But, you know, we learn rapidly. And certainly China especially learns even more rapidly, perhaps, than many of its rivals. I'll show you in a second where we're going next. First of all, the American project, the big new one for the moon, a whole new program basically to explore the far side using the combined forces of NASA and the Department of Energy. They're working together finally to do some cosmology. They've done it a bit before with microwave background, but now it's the dark ages that's attracting their attention. They'll launch this satellite, again a single dipole basically, in 2026. It's under construction now, and that will go to the far side. It'll stay there. It'll take data in the dark ages frequency range, 30, 50 megahertz. Unfortunately, it has batteries, but it doesn't have enough solar power to the batteries, doesn't have massive enough batteries to survive more than one night, one lunar night. So it's not going to get any science answers, we don't think. It'll be a great test experiment for future ones when we do develop better handles on how to power up our experiments. But so that's a step towards the future. But a much more interesting step, in my opinion, is what China is doing. So again, to be launched in 2026. This is the DSL experiment. It consists of 9 satellites in orbit around the moon, 2-hour orbits. So that way, no problem. You get your sunlight, you charge them up. When they go around the dark side, you then send your data back to Earth along with a mothership to correlate the data and send it back to Earth. So that's the project that will happen. And that's probably the leading contender to get this first signal of the dark ages at the moment. Okay, but, you know, that's just 3 years away. What else is happening? Well, in the longer term, it's getting exciting. Remember, I said we do need hundreds of thousands of antennae or more to get the ultimate signal, studying the fluctuations that tell us all about cosmic history and can help us test inflation. Without those, we can't do much. The global signal is fine, but it's not nearly enough. As with the microwave background, remember, we first measured Penzias and Wilson, the global signal, and then it took them a long, long time, several decades, to actually get the fluctuations. We may be entering that phase with radio astronomy too on the far side of the moon. And what is the future then? Well, here is the way you build up. Well, so one component is with ESA. They're developing a lunar lander. You can think of this as a delivery truck on the moon, and it can carry 1.5 tons, ready by 2030 or thereabouts. It'll be taking components to build radio telescopes on the moon. Here is one of the first designs for those. This has 128 antennae on the far side, laid out by lunar rovers along these strings of dipoles. Here's a more exotic one. So this is clever. This is the European plan. These are inflatable tubes. On these tubes are printed dipole antennae. And so these, their plan is to have something like thousands of these elements on the far side in a flat crater, and maybe as many as 10,000 eventually. And this will again be, the first step towards interferometer that will study the fluctuations. Even that isn't good enough. And so the craziest scheme of all, but it's futuristic. This is the sort of that will happen in who knows, 20 or more years. This one called Far View has 1 million antennae. And what is amazing about this design is that they are looking forward to being able to synthesize the wires, the antennae, on the moon. Because in the lunar regolith, you have all the elements you need to make steel, to make concrete, whatever. It's just a question of advancing our lunar factories, our lunar, operations, infrastructure to that point. And this again is a sort of you can forecast happening in a couple of decades. And astronomy should be one of the first to benefit from this sort of thing, because it's really simple stuff. Building 100,000 dipoles or whatever is one of the easier things you can do, right? Okay, and again, stepping forward, another plan. Okay, this is, you all know about Arecibo and the disaster that happened to it, and FAST, the Chinese version, slightly larger. This is a a radio telescope in a vast crater kilometers across. Well, one could do the same thing on the far side of the moon. They selected a dark crater 5 kilometers across. They'll have a deployable, a spherical, semi-spherical antennae, as in Arecibo, deployable will mesh inside the crater with a receiver suspended from the rims. And that will work at 30 megahertz. You don't need a very fine resolution wire mesh for the telescope at those low frequencies, and that will direct image the sources on the moon and help us figure out the problems of all these things getting in the way, the foregrounds that will stop us getting to the cosmology. So that's another part of the future planning. It's a design study at the moment, but it's one example of what we'll be doing on the moon in the years to come. Okay, a little bit of theory. So inflation has been this major boost to cosmology, but we have to test it. So there is a prediction due to the fluctuations it produces at the beginning, as the the gravity wave background is produced that we haven't measured yet, but it also gives it generates fluctuations and gives them a slight twist. We call this primordial non-Gaussianity. And there's a unique flavor to this non-Gaussianity, which comes in through almost generic inflation models. And you can think of it as a deviation from Gaussianity given by this strange parameter FNL, which is a deviation from the temperature fluctuations. And so you can see that FNL is a tiny fraction of, it's a second order correction to the temperature fluctuations. And it's been calculated for fairly generic, simple inflation models with the simplest, not necessarily totally generic, but simple models of fluctuations. And the number that comes out is, roughly speaking, 0.01 for this deviation, this second order deviation from Gaussianity. And it depends only basically on parameters you measure in the fluctuations, the scale of fluctuations. So that's a prediction. What is it we can do? Well, so here is where we are with the microwave background. It turns out our best value right now, our best upper limit right now on primordial non-Gaussianity is 10 in these same units. When I greatly increase the number of modes I have with galaxy surveys, it's predicted that we'll get down to unity, okay? But that's a long, long way from 0.01. And roughly speaking, because, the number of modes scales roughly is the, you want to get to this parameter, which is 100 of where we are now. We need maybe 10,000 times more information. And that we can do in principle with the radio. And that's where observing the radio at 21 centimeters will give us the information we need to reconstruct the fluctuations, look for the non-Gaussianity, and any complications associated with those, any interesting things that it will be much more complex than one single number, almost certainly. And this is sort of the way this goes. So early on with the microwave background, one generates fluctuations on this last scattering surface that we've measured so beautifully with the Planck satellite, for example. In the nearby galaxy surveys have been probably an enormous amount of data. These will all have built-in fluctuations, but it's in the dark ages, in between, in the hydrogen clouds, that we have all the real information content, and that, I think, is going to give us our best chance for testing inflation and getting down to numbers much smaller than we forecast being able to do from the microwave background or from galaxy surveys in the next decades with all our wonderful telescopes. Okay, so that's my first example. Now let me take you to a second example in cosmology, which is another long-standing problem. So the cosmic microwave background was mapped beautifully first by the Planck satellite, and what the FIRE-ASS instrument on Planck did as well, it was a spectrometer, a Fourier spectrometer, and it measured the deviations from a black body spectrum. And what it did was confirm this most amazing black body spectrum in the sky, one of the best that we can ever, achieve anywhere, actually, in the laboratory even. And so you can see here, these are 100 sigma error bars. Just incredible to look at this. And what we'd like to do is to look for deviations from black body, because we know it can't be a black body in cosmology, because you have structure formation, things forming from small to bigger fluctuations. Early on, the very small parts of the structure, there were fluctuations that came from inflation, but they're density fluctuations. They basically have friction against the background radiation. Early on, they must dissipate away, damp away, and they will leave you energy which imprints itself as energy injection into the spectrum of the microwave background. Now, when you inject energy in the early universe, if you do it too early, you just make black body radiation. It's not very interesting. But after about a month or so of the Big Bang, the universe can no longer process and redistribute the energy of the injected energy. And so you leave distortions behind. And basically, the further back you go, the smaller the structures you can test. And this roughly is a summary of what you can do. So what we've done so far with the microwave background and are doing now with all the galaxies is testing this end, the large scale end, and we'll be able to get to the small seeds from which all structure began if we can dissect the microwave background and look for signatures of this energy injection. So that's the idea. And it's now, how do we do that? We have to do much, much better than the FIRES experiment to look for this. And it's going to help us greatly that, again, there's so much information in the black body spectrum, as I will just now demonstrate to you. So here is the story. You can see, in principle, I talked about, trillions of these objects that are building blocks. Likewise, for these tiny galaxies, there are trillions of modes there injecting energy, and all this leads to rich information buried inside the black body spectrum, provided it's not perfectly black body and there's something left over. So this is what happens. This was pioneered by Rashid Sunyaev and Yakov Zeldovich not too many years after the discovery of the Planck radiation, and they said, well, when I inject early energy into the universe, I should basically, because it's injecting into in the Rayleigh genes into a colder plasma than the average, it'll get distributed, and you get a dip in energy here, an increase here. If it happens at early times or late times, you get slightly different forms for this. We care about the late time distortion, and it's measuring that is the guaranteed signal. It must happen because of the structure in the universe. So Kobe set these limits of order 10 to the minus 4 parts in 10,000 on possible deviations, just upper limits. But we know at some level there must be deviations because we live in an inhomogeneous universe. And here's the experiment that one could imagine doing, perhaps in the space, but probably most effectively on the moon. You go to a dark crater on the moon near the South Pole where the sun never gets high or low above the horizon. It's always shadowed and very cold and very dark, and it's a great place to put a Fourier transform interferometer. You basically have an instrument with a small telescope. You can just sit there at the base of the crater, stare at the sky, and as the moon turns around the Earth, you scan the sky, and basically you would compare a blackbody calibrator with the sky and look for spectral deviations. So that's the idea. You need just a 1.5 meter telescope to do that. And in case you need solar power, which you will do, these craters have very high rims. They're several kilometers high. They're always in the sunlight. So in principle, solar power is not too far away. So that's the sort of thing you could be doing. So we've tried to launch experiments, not on the moon, not so far, but in space as free flyers. One of them promised to do 3,000 times better than the Planck experiment, the Kobe experiment, FIRES experiment, and it was rejected by NASA. It was only a small telescope, that was the problem. It couldn't really promise to do new science, and there were technical challenges too. ESA is now talking, and you have to think of the long time scale here in their white paper for 2050, that one of their major priorities will be a large mission that would have such a spectrometer on to monitor the microwave background. But that's going to be in competition with many other missions. All sorts of other missions have priority over this. One's especially going to the outer planets, Jupiter, the icy moons, etc. Plus, these are the gravity wave emission, plus Athena, the X-ray emission, and each of these missions occurs every 5 or 7 or 10 years, so you have to wait a very long time for the next one of these missions. In the meantime, we'll be going, exploring the moon in enormous effort, and I think it'd be great to have sort of a pilot experiment like this, put in a dark crater on the moon. It sounds, and I'll explain to you in a moment just where the money for that might come from. But in principle, if you can do this is the sort of rich science you can do. You can, if you compare with the foregrounds, so that's this grey area, all the foregrounds of dust, infrared galaxies, many things. This was the FIRES you can do much better than FARAS. Okay, there are upper limits. You can work all the way down here to where the interesting things are coming in. Let me just explain what these curves are. So this is the excess in radiation, and this is the deficit. It's in quadrature, so this is what you're predicting in terms of mu distortions, the ones I mentioned. That's the green line. Actually, this is a weaker distortion, but this is the prediction of something. Again, to me, this is also a great thing to do, and that is the recombination lines from hydrogen and helium in the early universe. So the last scattering of the radiation, you started forming atoms, right, in the present atomic era of the universe. And as you formed those atoms, you formed in excited states, you got recombination again and again and again, because there were some ionizing photons around from the microwave background. And so basically you produce lines. And those lines are an amazing test of the history of the universe. All we do in astronomy practically is recombination lines. We study our Milky Way galaxy in terms of emission nebulae. You can actually do this for the universe as a whole. So I find that an exciting goal. Okay, let me try to assemble things for you in this picture of where we're going to go with putting together the building blocks of the universe. So this shows you the fluctuation story. This is all the way down here, suppressed by the power spectrum by 8 orders of magnitude, roughly 4 in the density fluctuations. It's equivalent. Are the Planck limits, but you notice they get very weak on these are the larger scales, because we just don't see enough different fluctuations of different sizes. But the most important thing is on the small scales, we lose resolution completely, and we have no idea what's going on over here. So we currently set limits from the FARAS experiment on the mu distortions. That's roughly passing 10 to the 4th. There are other ways of doing this, from absence of black holes, pulsar timing array. Let me not go into those. But the interesting thing is looking to the future. Now, when we have these new types of exploration, first of all, we're going to do the dark side. Okay, and in the dark side, we're going to measure the 21 centimeters. That's over here. I've got these colors mismatched. And then with the microwave background, we're going to measure this as well. So we're going to fill in the entire gap that we had before, from large to smaller scales, and really get the formation of structure down completely, understand much better the bottom-up theory, the cold dark matter theory of formation, and at the same time we'll have this wonderful probe of inflation. So all that is the future of two types of experiments, radio astronomy and far infrared astronomy, in the next decades. Okay, so there are one or two more points here that I want to make. So what I've described to you is really compelling science, which I think is a reason why, when you design any new mission in space or anywhere, the first case you have to make is that the science you want to do is compelling. Okay. Now, you don't just go to the moon because you want to go to the moon and, play golf or something. You have to have really strong science goals. And I think astronomy is giving us very compelling science goals. So that's one reason I'm excited by this. And likewise, you could make a similar case for the cosmic black body radiation. And here, for example, you can see where we've previously been on the moon, the near side. These are the various Apollo landing sites. There is the one Chinese landing here, and we're probably near the poles of the moon. You can see there are many craters, great places, the North or the South Pole, for doing astronomy. Okay, so what sort of astronomy am I talking about? I just want to show you very briefly the future of astronomy as well on the moon. And these, again, are things that you cannot really dream about even, or barely dream about from doing from the Earth or in space. Okay, so first of all, the moon is a gigantic bar with very low seismic activity and a wonderful gravity wave detector. So when gravity waves come from far away, the moon oscillates slightly. Now, we have gravity wave detectors, and so the pulsar timing array, hundreds of millisecond pulsars, their glitches attest to a passing gravity wave. LIGO, Virgo, currently the two interferometers, third one in Europe, two in the US, one in Japan about to start, one in India will start in a decade or thereabouts. All of these are going to measure this part of the frequency spectrum, looking for black hole mergers and other types of exotic activity. LISA, 3 million, these are 4 kilometers across, right? And that determines the frequency they work at. LISA is 1 million kilometers, 3 satellites in space. That's going to get the low frequency band. If we can go to the moon, then something new happens. We're opening up the several thousand kilometer scale. That means frequencies in between LIGO and LISA. And this way you can watch the black holes merging together, emitting gravity waves, and gradually giving you their final chirp as they finally merge together. It'll fill in the whole history of gravity wave astronomy. So that's the hope for the moon. Okay, so that's one plan, and people are seriously considering this now, different schemes for seismometers on the moon. The second thing is that on the moon, you can build big telescopes because gravity is 1/6 weaker than on the Earth, so you don't have the same stresses, not the same atmospheric issues. And so in principle, we've failed to build a bigger telescope than 39 meters on the Earth. But on the moon, there's nothing stopping us to build a 100-meter telescope. This is a design for one. And what could you do with those telescopes? Well, the yield of exoplanets goes up enormously. The deeper you look, the larger your surface area. So our current hope, best hope, is a telescope called LUVOIR. It's got a slightly different name now, but it was proposed by NASA in its last major survey, the decadal survey, the current one. And they decided that a 6-meter telescope was the best one could do, given any foreseeable budget, in space, with spectrometers and coronagraphs designed to look for life in atmospheres, okay? And they will have of order 25 Earth-like planets within the nearby tens of parsecs. So that's all they could do with a 6-meter telescope. But if you have a 100-meter telescope, you can suddenly get thousands. Now, we've no idea what the chances of life are, but you could bet, that going from a small number, your chances are going to be smaller. If you can go to hundreds or thousands, you might be in business for looking for interesting signatures of life. So that's the reason for building a big telescope on the moon. But the even more amazing part of the story is that this, is a monolithic or multi-dish 100-meter type telescope over there that could get us up to large aperture. But that's what I call Owl Moon, okay? But you could do something more incredible, and that's this. You could build a 5-kilometer telescope on the moon. And the idea is to go back to your idea of a dark crater, and you string a series of 5-meter telescopes across the surface of the crater in a sort of a hemispherical array. You just need 50 or 100 5-meter telescopes. They'd look probably in the near infrared. And what the clever thing you have to do is you have on the rims, you suspend the focal plane, the camera, and you have to have a very clever way of combining the beams. Now, this is just a question of having a quantum type beam splitter to give you coherent beams, and then you can do images. Okay, so in principle we can do this. It's technology that's not quite here yet. We've done it for 2 telescopes, but doing it on this scale would be a little harder, but the principles are understood. And with that technology and kilometers across for your baseline, you can get micro-second precision in your optical or UV images. Okay, and you could resolve, this is one of the most promising exoplanet systems, 40 light years away, and the TRAPPIST system with some 8 Earth-like, they're thought to be Earth-like exoplanets, but that's all we know from the temperatures and positions, etc. You could actually image them and look for interesting signatures like seasonal variations or more complex biological variations in their atmospheres. So that'll be even more incredible things. So that is sort of the future one can imagine for exoplanet astronomy, which is one of our greatest pushes forward into the future at the moment in astronomy. So it's not just cosmology, it's many, many things in astronomy too. Okay, so I'm going to summarize now with a couple of points. One is that the whole field of lunar science is undergoing a renaissance. The reason for that, well, I've told you about the low frequency radio projects being planned, but the reason this has really happened is that it's become, over the past 2 or 3 years, much easier to launch into space and to the moon. there are many commercial providers now. Why, just 2 weeks ago, the United Arab Emirates was trying to land a robotic craft on the moon by a Japanese launcher. Okay, so it didn't succeed, but that gives you the point that lunar landings are now within the reach of anybody practically who wants to go to the moon. And it's only a matter of time. Now, they can carry fairly small payloads. It's only a matter of time because we'll have the likes of Starship being constructed. It hasn't flown successfully yet, but it will do soon. And that'll give you large payloads at low cost. So the whole landscape, I should say moonscape, is about to be changed for doing experiments on the moon and science experiments in particular. And I mentioned this ESA lunar lander, which is basically, if you like, a delivery truck for taking things to the moon, and that would have to be launched by a large launcher. But that's soon going to be happening, and it means the whole landscape out there for the moon is changing. And you can see here is the scale of things. We're now talking about tens of tons more. The current Vulcan spacecraft of SpaceX is it's about to launch Euclid, for example, in July. And we can look forward in a few years to having much larger launches and reusable launches, such as Starship, which will make a delivery to the moon fairly routine, actually, and inexpensive. And that'll be needed for the future NASA programs for landing on the moon, too. Okay, so the telescopes, actually, I don't think astronomers should be too greedy. Maybe pick one of these craters, dark craters near the South Pole. They're wonderful sites for imagining doing astronomy. Let me just show you, I can't resist showing this. This is the craters are so high that there's always sunlight on them for these South Pole craters. That means you have solar power. There's water on the moon. Thanks to an Indian spacecraft, Chandrayaan-1 discovered hydroxyl molecules on the moon. So India is very much in the game of lunar exploration. Now finding the ice on the moon is going to make things much harder for the astronomers because there aren't that many sites you can go to on the moon for doing major experiments, putting major telescopes. And the reason is you need a flat surface, you don't have the crater sides that's too steep, you have to be able to get into it. You don't want to land in the crater because that will pollute the crater terribly. You have to get in there somehow. With lunar rovers, all of this is, means that you can't just choose any random place to go on the moon. To do a telescope, you want a crater with mild slopes and so forth. And you want to make sure maybe there isn't too much water in the crater, too much ice, because otherwise you'd have the mining companies coming to you to say, we want to do the mining. And they have much more motivation, even the astronomers, because there are many billions of dollars at stake there. And they would probably have priority in the realistic scenario over the astronomers. We'd be lucky to get one crater to ourselves, which would be chosen perhaps to be a dry crater without ice deposits, so not too tempting for the commercial sector. Anyway, those are all issues we'll have to come to. And there is one final point, and that is that the politics of the moon. I thought it interesting that I should mention this, because we have several countries jostling really for space on the moon. It's not just China and the US. I'm sure that India's got its eyes on the moon too. They've been talking about surveying experiments to do geological surveying of the moon, to look for potential that would be used, I presume, for potential mining sites. It'd be very valuable information too. So all those are things, and the smaller countries can be involved in similar things too. It's not that hard to send a satellite taking images of around the moon. And that's the sort of thing many people will do. And it'll bit like surveying for oil was in the old days, I imagine. Now, on top of that, you've got issues that are legal issues. Who gets there first to a certain crater? Is it my crater? Is it your crater? You have to have some international rules. There was a space treaty that I think India most likely co-signed. 100 nations did in 1967. And it has all sorts of nice words in it about don't pollute the moon, no military on the moon, etc., etc. But one thing is missing. There's no enforcement. So how on earth do you lay that down? Do you that's something that must be discussed internationally in the next few years, how you can enforce use of the legal rights to property, to mining zones, criminal law, all these sorts of things. And finally, the pollution will be a serious issue because you can pollute with mining the surface of the moon, you can pollute the dark craters, you can even pollute the sky because there'll be many small satellites going around the moon to communicate back to Earth. So all of this can be controlled, and we have a nice period now of a few years to figure this out. I'm optimistic that we'll do this, but it's not obvious at all. You want to avoid having the Wild West on the moon all over again, but everyone competing for whatever. Okay, so hopefully 2040 will be when we'll be doing lots of this. And the final argument I want to tell you is that your reaction of many people is this is absurdly expensive. We can never afford this, but that simply isn't true. And the reason is that think of the Hubble Space Telescope, and indeed any number of other telescopes launched by the Space Shuttle. We'd never have had those telescopes. It would have been far too expensive for us had it not been that we had a space shuttle and the International Space Station. Those things cost multi-billions, okay? The Space Telescope was a few percent of that. It was a little bit like the cream on the cake. And I think it'll be the same for the moon. We're putting so much energy, so much effort into infrastructure that building the telescopes will be such a more perturbation of the total that it's not crazy to think about it. And historically, if you look back and see in the Apollo era, 5% of the US national budget went to the Apollo program for a few years only, and then it settled down. So now we're down to 0.5% or something, and I don't know what the fraction of the Indian ISRO budget is, your gross domestic project is, but it can't be that trivial. And the Chinese, etc., etc. All of this is, we're down at the 1% of GDP level, but that's enough to all of the projects I'm talking about. So it's, I think we really can get there. And to summarize, we have a space-like environment. We can do radio astronomy, we can do far infrared astronomy, gravity waves, and we can tackle the whole future of astronomy and cosmology. And now's the time to start planning for this. So, thank you. By the way, that's an advertisement for a new book that's just come out, so I recommend.
Given the fantastic advantage to have a gravitational wave detector on the moon, how practical is it to have a gravitational wave detector on the moon? Do you need multiple human landing? So I was wondering about it.
I think one landing could do the job. Look, all we're discussing in some of these projects, putting seismometers, 3 or 4 seismometers, a few kilometers apart in a dark crater on the moon. These are state-of-the-art seismometers, rather better than the Apollo ones, but nevertheless we understand them, we've built them, etc. So you have to, be able to coherently have fiber cables connecting them to try to synchronize the signals, etc. But none of this seems really, really hard to me. So it's one of the more exciting experiments that doesn't seem to have too high a technological threshold, and also not a huge expense either. One would need a lunar rover to just, take them around the dark crater, etc. All of this is being planned. There'll be any number of lunar rovers waiting for us to use on the moon. So that's the first thing we'll be doing, is driving around the moon, our future cosmonauts.
Yes.
Hey, very nice talk. If we detect these number of sources at redshift 50, I could understand that maybe we can understand inflation, but how would that give us more understanding of dark energy, and also like dark matter? What is the component? What are the properties? How would that help in that? Like these H1 sources at redshift 50, how would that help in?
So I think that's going to be really difficult. I don't really see the future about coming to convergence on dark matter or dark energy. That's all I was arguing, that there's no evident end in sight. There is an end in sight for testing inflation if I take this lunar 21 centimeter dark ages strategy. So that's the only difference I'd like to make, that one has a guaranteed return scientifically. It may be very hard to get there, but there is something at the end of the road. Whereas for dark matter, we have no idea. Maybe there is something there, but how far away that is, how weakly interacting that is, we have no idea whatsoever.
I had a question about dark matter. So it is dark because light doesn't couple to it, and we are not able to see the signatures of the matter directly by observation. So, is there a limit that is posed from all the observations which exist, which says this is the upper bound on the interaction of light with that matter, given that we know we can assume the abundance of the matter due to gravitational signatures? What is the limit of the coupling of electromagnetism to the dark matter from observations?
Yeah, so there are several different types of coupling you could imagine via charged particles or dark matter via photons or neutrinos, all these things. And so people try very hard to set limits on what these interactions might be. And if they were too strong, you would get some signal that we might have seen already. So there are upper limits out there, but they seem to get better and better every year as people try harder. So maybe someday we'll get to the limit of what limits we can set, and it's because we even find some signal that we can say, this glow is dark matter, but we will see.
Yeah, thanks very much. That was a very nice talk. I don't come from the field of cosmology or astronomy, so I'll dare to ask you a question which is part philosophical, part practical. All these experiments that you are motivating, they would help us know more about the origin of our universe. So how do you actually, justify doing them? In the sense that, in today's day and age, we are forced to think of making products. For everything we want to do, they say, what is the product? At least in India, there seems to be a trend that, basic science or fundamental science is something which is okay, but where is the product at the end of the day?
Yeah, I think that's a bit unfortunate. You have to go back to your roots. And in India, a long time ago, we were very worried about the origins. And the same is true in Greek civilizations, whatever, you name it. Maybe we've gotten a little bit frightened away by all this technology. But I think at the end of the day, if all you're going to do is improve your technology, you're missing something. I mean, there's something greater, more important out there as well that you should be looking for, some vision you have of the universe. We should be trying to understand it. Many of us are. And persuading the politicians is a whole other story. But I think some of them do listen, that they are excited by these adventurous new projects that we want to do in space. They get so much publicity, it benefits everybody at the end of the day, both funding and the politician support. So I think there is even a return there as well. And it's wonderful for education, obviously, as well. That goes without saying.
Thank you. Thank you for the answer.
If I understand correctly, that the main point of the moon being a perfect site is radio quiet and several other suggestions. So my question is that, of course, setting up this or a series of experiment like this is resource and consuming in terms of many things. So how difficult is it in Earth finding a place or creating a radio quiet zone vis-a-vis finding, for example, advantage in moon? I mean, in that context, I wanted to understand. So I'm sure there are places in Earth where it can be perhaps made a little more radio quiet.
The trouble really is, as we develop resources on the moon, we'll be putting up satellites, many satellites, as around the Earth. And so we'll be polluting the radio sky and the optical sky from reflections of light, sunlight from the satellites. So there are ways to control that. You can design your satellites with special reflective coatings to avoid scatter. So we've somehow lost control of that on the Earth right now. There's too much commercial pressure. But on the moon, if we have tens of years to plan ahead, we could probably do this. Getting radio quietness is more difficult. You want to allocate certain frequency bands for the commercial uses and some others for the astronomers. And that way you could probably do things. But again, all this needs some sort of central planning, which I hope we get.
Any further questions? Yeah.
The idea of using moon to detect gravitational waves, I guess, is the idea to detect the normal modes of the moon excited by these gravitational wave, or is it some ranging kind of measurement?
Okay, it's more than just the normal modes. That you can get higher harmonics as well, and I think there are clever ways of combining interferometric and seismometer type detectors to get even a broader range. I mean, people are looking at this very carefully, but it's not just normal modes.
Any further questions? Actually, I had one. So when you talk about exoplanet imaging, right, by having these kilometers of craters, what's the kind of limitation we would hit just because the surface itself is not completely smooth and it has its own perturbations for the craters? So would that be the ultimate limit on the resolution that one can achieve for exoplanets?
I would guess you can probably control that to some extent. Ultimately, it's combinations of beams and optical delay lines, the sort of thing that you have to control. And once you can control that, then I think the surface irregularities will be a minor issue.
Okay. Any last questions? If not, then let's thank. Okay.
There's one there.
Yeah.
Given that there are a lot of lunar missions being planned in the future, what do you comment on the space debris or the lunar debris in future?
Yeah, we have a debris problem around the Earth now, a serious one, but it's limited to a fairly narrow range of heights around the Earth. So basically, and many of even the smallest bits of debris are charted very carefully by NASA and other organizations probably. So I imagine on the moon we will just have to be a little more careful and try to control things better. But again, that needs some international coordination, which so far there's no sign of, but hopefully that will happen.
Questions? Okay. Let's thanks Joe again for a great talk. Very inspiring. And I request Tarun to please present a souvenir to a speaker.
Oh, thank you.
Pictorial background.